All right, let's talk about one of the most powerful and fascinating engines on the planet, the gas turbine. These things are absolute monsters of modern power and speed. But as you're about to find out, not all gas turbines are created equal. In fact, we're going to put two fundamentally different designs head-to-head in a real engine showdown.
So, let me ask you a quick question. What single piece of technology is so powerful it can launch a fighter jet off an aircraft carrier, but can also be scaled up to generate enough electricity for an entire city? Well, believe it or not, the answer to both is exactly the same: the incredible gas turbine.
Now, the amazing thing is, the basic principle is actually pretty simple. You can think of a gas turbine as a super sophisticated air-moving machine. It just sucks in a massive amount of air, compresses it down, heats it up like crazy, and then uses all that expanding hot gas to spin a bunch of blades and create just immense power.
Okay, so let's get right to the heart of it. Because even though that core idea sounds simple enough, there is one single, fundamental design choice that splits the entire gas turbine family into two totally different branches. It really changes everything.
And it all boils down to this one simple question. How do you actually heat that compressed air to make it expand and spin the blades? The answer to this one question is the fork in the road that gives us the two main contenders in our showdown today.
So, first up in the ring, we've got the direct-fired gas turbine. Let's just call this one the impatient purist. It's the design you see most often, and it's known for being really efficient and pretty straightforward. But, as we'll see, it is also very, very picky.
Here's the play-by-play. Step 1, the compressor grabs air and squeezes it tight. Then step 2, in the combustor, fuel gets injected and lit on fire directly inside that pressurized air. It's basically one giant high-pressure combustion party. And finally, step 3, that super hot, high-energy mix of air and exhaust gas just blasts through the turbine, spinning the blades at incredible speeds.
Now that direct approach gives it some huge advantages. You know, its simpler structure means it's cheaper to build up front, and burning the fuel right there in the airstream leads to really high efficiency. But here's the catch. Because that fiery explosion is happening right inside the engine, it can only handle super clean fuels. Any kind of impurity, like ash, would basically act like a sandblaster and just shred those delicate, high-speed turbine blades to pieces.
And that weakness brings us right to our second contender, the externally fired gas turbine. This is the flexible workhorse. It's a bit more complex, definitely less common, but it is unbelievably robust and adaptable. So this process starts the same way. The compressor squeezes the air. But here's the absolutely brilliant twist. The compressed air never actually mixes with the fuel. Instead, it gets sent into this special component called a high-temperature heat exchanger. You can kind of think of it like a car's radiator, but in reverse. Then, in a completely separate furnace, the fuel gets burned. That fire heats up the outside of the heat exchanger, which then superheats the clean air flowing on the inside. That pure hot air is what goes on to spin the turbine. The key takeaway here is that the dirty combustion gases never ever touch the core of the engine. And this separation, well, that's the externally fired turbine's superpower. It gives it incredible fuel flexibility. I mean, you can run this thing on solid fuels like coal or biomass, dirty liquids, unrefined gases, stuff that would destroy a direct fire turbine in seconds. So what's the trade-off? Well, that big heat exchanger adds cost and complexity, and heating the air indirectly means you do lose a little bit of overall efficiency.
So there you have it, the efficient purist versus the flexible workhorse. Let's put them head-to-head and really see how these two different ways of thinking play out in the real world. Right off the bat, the biggest, most game-changing difference is fuel. The DFGT is a seriously picky eater. If you want to use a dirty fuel, you first have to build a whole separate, expensive, and complicated cleaning system for it. The EFGT, on the other hand, eats pretty much anything you throw at it. Solid, liquid, or gas, no extra cleaning needed. That is a massive, massive operational advantage.
And this same design choice completely changes the maintenance game. Think about it. If something goes wrong inside the combustor of a direct-fired turbine, you're looking at major surgery. The entire engine has to be dismantled. But with the externally fired turbine, since all the messy stuff happens in that separate heat exchanger, a problem is often just a minor procedure. You can pull out and service a single heating tube without ever cracking open the main engine. The difference in downtime and cost here is just enormous.
So let's look at the final scorecard, shall we? The direct-fired turbine, our purist, it definitely wins on lower initial cost and slightly higher peak efficiency. But the externally fired turbine, our workhorse, is the undisputed champion of fuel flexibility, and it has a much simpler combustion process. It's a classic engineering trade-off, right?
Do you want peak performance, but only under perfect conditions? Or do you want robust flexibility that can handle just about any situation?
And that leaves us with a really fascinating final thought. For decades, the efficient, direct-fired turbine has pretty much dominated the market. But now, as our world is desperately searching for more diverse and alternative energy sources, everything from biomass to industrial waste and even synthetic fuels, could the more complex but incredibly adaptable externally fired workhorse finally have its moment and become the true engine of the future?